When we want to evaluate VR interaction techniques on ergonomics, we usually have to conduct expensive and time-consuming user studies. In this work, we propose one way out, that is, biomechanical simulations. But to be able to run those simulations, we have to view HCI as an optimal control problem. I will explain how this works on this small example. So when the user on the left tries to control this virtual object on the right by moving the VR controller, they choose muscle control signals to move their body. This movement is then sensed and transferred to the system by the input device. There, it moves the virtual objects and depending on the interaction technique that is applied. This movement is finally sent back to the user through, for example, the head-mounted display. Now, we can model this whole loop as a set of differential equations that we call the human-computer system dynamics that will tell us how the states evolve over time when we apply certain muscle control signals. And the states hereby are a combination of the user states, for example, the joint angles, joint velocities, the input device states, the position of the VR controller, or the interface states, so for example, positions of virtual objects. Now, the user has to find out which control to choose in this situation. And this highly depends on the task, but also on personal preferences. As we assume that humans are rational acting agents, we assume that the user will try to optimize some internalized cost function J that depends on the current state and control signals. Now, this optimization must happen subject to the constraints posed by the human-computer system dynamics. For example, the body of the user can't move in another way than their biomechanics allow it to. If we are able to model this system and then solve the optimal control problem, we can obtain a simulation of the whole human-computer interaction loop. But to solve this optimal control problem, we chose to use Model Predictive Control, or MPC, which is a classic method in mathematical control theory because it can also work with nonlinear systems. MPC works as follows. So instead of optimizing the cost function J for an infinite time horizon, we only optimize it for the next n time steps by minimizing this sum of stage costs L. We also do that subject to the constraints posed by the human motor system dynamics, and we start at some initial state x0. Now, when we solve this optimal control problem, we obtain the so-called open loop optimal control, U star, and that, when applied, can be seen as the prediction of the states as seen by the user. Now, instead of just blindly following this plan, MPC only applies the first part of this control, obtaining a new actual state, x1, that can differ from the one that we planned with because of some unmodeled uncertainties and disturbances in the, for example, motor control noise. Now, when we continue, we just move our MPC horizon by one time step and then do the same optimization again. We follow this, we can terminate when we reach our goal. Now, the left part of this graph that you can see here is actually a simulation of the interaction because it contains all the information about the user states, the device state, and the application states, as well as the user's actions over time. And there are two things that we need to model here. It's the human-computer system dynamics themselves on one hand, and then the cost function that a user tries to minimize. For the system dynamics, we chose to take a state-of-the-art biomechanical model that we implemented in fast physics simulation Muchoko. And this model is nonlinear and joint-actuated, but we also applied a second-order muscle model to obtain this time delays that are present in muscle control. For the input device, we chose to model a virtual motion capturing marker on the fingertip that we can then use to apply different interaction techniques for pointing. For example, here this virtual cursor that just applies a translation on the fingertip position. And this already concludes our human-computer system dynamics. Now, to model the cost function, we have to think about the task. And there we chose a classic ISO pointing task in VR, so the user can see those 13 targets in front of them and has to move the virtual cursor to the active target. To model this, we chose 3 different cost functions. The first one and simplest one is just distance and control costs. So we penalize the distance of the current cursor position xpk to the target p star. And then on top of that, we add a term that penalizes high control effort. And this term is also weighted by a parameter R1 that we can increase or decrease depending on the user's preferences. As a second version, on top of this DC cost, we added a commanded torque change cost term that is commonly used in human motor control. That also penalizes a change in the joint torques that comes directly from the muscle control signal. And a third variant that we evaluated was instead of the CTC, we added a term that penalizes the acceleration in all the joints. It is less commonly used in human motor control, but can be explained with the fact that high acceleration in the joints also causes high strain on them. Now, these cost functions all involve different cost weights that we need to design. And since our goal is to model human-like movements, we decided to run a small user study with 6 participants and to find some reference data. Now we have 4 conditions here, that is 2 different versions of a virtual cursor and 2 different versions of a virtual pad, and we conducted 65 movements per condition. Now with this data, we can actually compare our simulation results, so XQPOS, which contains all the joint angles over time, with XQPOS head, which is the corresponding real user movement over time, and calculate a root mean squared error to define how well our simulation does compare to the user. And to find the best cost weights now, we run 5 different simulations and with 1 fixed cost weight par R1 and R2, and then calculate the root mean squared errors against the real user data. We use this cost function for a CMIES to obtain cost weights R1 and R2 for each condition and each participant. Now that we have the cost weights in place, we also wanted to know how much impact those have on the actual simulation trajectory. So in this example of the joint acceleration cost, we can see here the projected position time series of the cursor. When we fix the effort term weight R1 and increase R2 over time, and you can see that the movements become slower and slower as expected, but also the overshoot increases, which is probably due to the fact that slowing down the joints also increases the cost. Now, when we do this more elaborately and we compare different cost weight pairs R1 and R2 on the resulting root mean squared error when we evaluate the simulations with real user data, we can see that there's a smooth dependency This raises the hope that even if we didn't find the perfect weights with our parameter fitting, but we are close at least, and that we also would have a quite good performance in the simulation. Now that where we have the cost weights, we can actually compare our 3 different cost functions with each other and against user data. So in this video here, you can see on the left side a replay of real user data and 3 different cost functions. Just one thing that I want to point out here is when looking at the distance and control, the DC, you can see that it has some problems reaching the targets that are high up. That is probably due to the fact that in order to obtain movements that are as slow as human movements, you would have to increase the effort cost term in a way that reaching the targets high up gets too expensive for the model. If we do a quantitative comparison of those 3 cost functions, we can see that joint acceleration costs actually outperform the other 2 in cursor positions as well as in joint angles. That's why we continued all our evaluations with the joint acceleration cost. When we evaluate our predictions now with other users, we can see that our predictions are actually within the between user variability, meaning that if we use our simulations to predict the movements of one particular user, this prediction is as good as if other users would try to predict this one user. In joint angles, we can even perform better than the other users, but that is mainly due to the fact that our simulation has a biomechanical model of this particular user, and other users may have different physiologies. We can now use those simulations to evaluate interaction technique parameters prior to conducting user studies. In this example, you can see a virtual pet simulation where the fingertip is just projected forward. Then now when we move the cursor also upwards, these movements are done with a lowered elbow, which would increase the ergonomics. To produce those simulations, there's one important parameter of MPC that we need to fix. This is the horizon, meaning like this prediction horizon that we chose. And we can show that for this specific pointing task, a horizon of 10 that is around 400 milliseconds is enough for a movement that takes 700 milliseconds. Also increasing the MPC horizon would also increase the computation time, and we can see that when we compare our simulations with the user data, increasing the MPC horizon over 10 does not increase the performance. To conclude, we have seen that HCI can be seen as an optimal control problem, and then we can apply nonlinear biomechanical user models if we choose the right cost function, like we did here with the joint acceleration cost. We can actually predict mid-air movements within the between user variance. So where can we go from here? For example, we could generalize those simulations to various interaction techniques, tasks, or users. Or we could use our simulations in an optimization loop to optimize interface parameters. So we could run a simulation, collect the user data and motion data, then automatically update parameters to improve performance, for example. Or we can run that online to adapt interaction techniques while the environment around the user is changing, for example. With this, I want to thank you for your attention, and feel free to get in touch either via mail or check out my website, where you can also find the code for this work.